Hey, what's up, guys? Yeah, so welcome to my analytic number theory video. So today I want to talk about the original series and the Euler product. So if you haven't seen my analytic number theory lecture, I will post the link below so you can check. And I think this is the true meats and the true hard parts, the true key idea in I think it's the famous number theory results like prime number theorem or other uh, uh, beautiful technique that you can try to connect the complex analysis. So you can view this Dirichlet series ideas that try to connect the complex analysis idea into the number theory. So for example, if you want to prove the prime number theorem, which is the pi of x, is approximate x divided by log x. If you want to prove that this kind of thing, you need to you can use the Riemann zeta function, right? So which is each arithmetic function will correspond into something in the number theory complex analysis, and you can transform it back. So this is a very beautiful idea. So I want to share with you guys. Okay. Okay, so let me just quickly. So in this video, I want to give a definition of the original series and discuss some examples. And I will also talk about the Euler product. Euler product means that okay. So I will talk about I will talk in the future. Okay, so the idea is that the definition. Let's start with some arithmetic function. So remember, arithmetic function is from integer to complex number, and you can define capital F to be f of n of s, and from 1 to infinity. Okay, so without loss of generosity, so we will add, so s can be a complex number. Okay, so f will be a complex number to a complex number. Okay, and we need to assume that so this f of s, capital of S, defined when series absolute convergence. Okay, so this is just the Dirichlet series. Okay, so that's the trivial example, which is you just take f of n to be 1 for all n, then you get f of s to be this. Okay, so this is a famous zeta function. Okay, so before I keep going, let me just quickly prove the results. Okay, so remember that previously we in the number theory, I also described so-called Dirichlet product. So the idea is that somebody give you, let's say you get two arithmetic function, then you can define h of n to be, let's say, f of d, g, n divided by d, where d divides n. So this is called the convolution in the number theory. And I also claimed that previously, I think I proved this convolution will give you a group. It'll give you a group structure. Give you a group structure. So if you haven't seen this, I would recommend to see my previous video, and I will post a link below. Okay. Okay. So very simple proof. There's a theorem that let's say you f, right? You mapped into f, and the g you map into g, and which this is a two Dirichlet series of corresponding arithmetic function. Then you can prove that f of s, g of s will be, let's say, f of k, g of m. Just write the products. So kmn, ks, which is 1 over n to s, from 1 to infinity. So you can share it. So it becomes, let's say, km equals to n. So it's this is just 1, and the f of k, g of m. Okay, so this is just define km to be, combine km to be n, and n from 1 to infinity, and the sum of this. Okay, so if you see this is just f g, right? Okay. Okay, so which tell you that which give you what I'm saying. So this guy is actually h of s by consider this h. Okay, so this tell me that the Dirichlet series actually is a convolution of Dirichlet series, give you a Dirichlet it gives the Dirichlet series of the Dirichlet products. Okay, also there's a theorem that if f of s, g of s converge, I should say absolute converge, let's say for some sigma, then the f of s, g of s, defined as g of s will also converge. Well, this is trivial, right? Because by definition, right? But it's not likely that, right? Because you exchange coefficient. So you can easily check this. Let's say consider this. This is this, which is n of s, n from 1 to infinity, bounded by f of k, g of m. By the way, this equation is trivially this guy converge, but this guy equals to this is not non-trivial because we already do the exchange of the we do the exchange, right? So you know that if you somebody give you a series which may be alternating, if you change it, you will change its convergence if it's not absolute converge. Okay, so k equals n, you can bound it, right? So this guy is less equals to, you can separate into this, right? You get f of k, k to s, k from 1 to infinity, okay, and m from 1 infinity, so g of m, m of s. Okay, so if these two both are absolute converge, then this guy converge. Okay, so this proves our results. Okay, so now we can play around with this Dirichlet series. Okay, so let's talk about many examples. Okay. Okay, by the way, let me just quickly one can also define the so-called the inverse of the Dirichlet series. Okay, so for example, let's say f of s, right? You can define another function g of s, which is 1 over f of s. Okay, and you can, okay, so this looks a little bit stupid, right? Because you just say something, say 1 over f, right? But actually, you need to think a little bit that how I come up with this g in terms of how I can come up with this g in terms of arithmetic functions. Right. So the idea is that so the proof sketch. Let me just sketch. Right. So basically, you can try to expand it and solve the coefficient 1 by 1. Okay. So this is the idea. So you can solve the coefficient 1 by 1. Okay. Okay. So let's do some trivial. Okay. So the first one is a Uni function, which is very trivial. So if n is 1, if n is 1, if n is not 1. Not 1, then you get 0. Okay, so your Dirichlet series will be 1. Okay, so f of e, now f of s will be 1. Okay. Right, because this is just this e of n, and from 1 to infinity. So this is non-zero when n equals 1. Okay, so Mobius function, also famous in the number theory, is mu of n. Mu of n is defined to be what? Okay, it's defined to be, let me see. Okay, so if, sorry, I'm stupid. So if n is you need to count n has how many distinct primes, right? So if n has r distinct prime, it's -1. If n has even distinct prime, which is 1, otherwise 0. Okay. And previously, I think I proved the results that if you sum over, if you do this, okay, then you will get 1 over zeta s. Okay, so this is the, I think why previously has a video that try to compute like try to find the Euler functions, right? But bound of Euler functions, which will use this equality. So this is a definition, right? You can write the zeta function into the Euler product, and you can prove these results. I guess this is not difficult. Okay. Okay, and then there's a function like a so-called square functions. So 3 square function. So square function s of n is defined to be 1 if n is square. So 1 for 9 something and L 0 or else. Okay, and then you can do this. So what is this? You just spend it out, right? You get this 1, 4, 9 s, right? So you do this, and you will see, this is just zeta to s. Okay, you can check by yourself, right? Because this guy can be written as so this is 1. I'm stupid. So this is 1 divided by 2 to the 2s, and 1 divided by 3 to the 2s. Okay. So now, if you want to find a number of square, then you can do the same thing. If you know let's say you know the behavior of this zeta s. Okay. So number 4, which is very important. Okay. So one is the this log function. Okay, so obviously this guy is the derivative of zeta function, right? Because the zeta function is this. Okay, but we want to. So previously I also define this main goal function. Sorry, maybe I spelled it wrong. But this main goal function defined to be lambda n, which is if n is a prime power, which is 1, else is 0. So it's not 1, it's log p. Okay, so log p if n is p to a prime power, otherwise it's 0. Okay, and I also proved that this has a very strange relation such that this lambda d divides n will give you log n. Okay, so if you see this carefully, what you got is what? What you get is that this lambda convolution with the identity function will give you log n. Okay, so you can, if you do this, then what you tell is that this lambda, the convolution of this lambda, the divisional series of this lambda and the divisional series of this 1 will give you this. Okay, so the divisional series of this 1 is what? It's zeta s. Okay, so okay, so you get something which is this. Okay, so which you just prove these famous results in the analytic number theory that we will employ this. Okay, so this function will give you the prime number theory in the future. So in the future, I will start from this point. Okay, so this is the main goal function and the connection with the log function. Okay. Okay, so now let's talk about Euler phi function. So I think I already talked about it 10 times, 100 times of definition of Euler function. So I will skip this. Okay, so you can, so this. Okay, and this is non-trivial, very non-trivial. The proof is zeta s minus 1 and zeta s. Okay, so the idea is that I think our previous, also in the previous video, that I proved the Euler function is the convolution with identity and the Mobius function. Okay, so you can check this. Will give you this. Probably not very trivial, but you can try to do this. Okay. Okay, and also the next one is a divisor function, which is d of n is a number of divisor. Okay, so number of divisor. Okay, and obviously that so d of n is just what? It's just this d of n 1. So it's just one convolution 1. Okay, okay. So you take the Dirichlet series, you get a Dirichlet series of this. This guy is just a Dirichlet series of 1. So it's zeta s squared. Okay, so now you find the interesting thing is that it seems like that every function in the analytic number theory is miraculous connected to the zeta function, which is weird. Okay, so divisor function connected to zeta function, Mobius function connected to zeta function, Euler phi function connected to zeta function, Van Gogh function connected to zeta function. So everything is actually connected to zeta function. Okay. Okay, I think this is okay. Yeah, this is enough. Okay. Okay, so let me just talk about quickly introduce the Euler product. Okay, so what is Euler product? Okay. What is Euler product? Okay, so so originally let's say f of n, right? So somebody give you a arithmetic function, then you can stupidly put this f of n divided by n of s and from 1 to infinity and then say, oh, this is f of s. Another definition is that you come up with another function, which is you put a sum over prime 1 over summation n from 1 to infinity f of p to m p to ms. Okay, so this guy is defined to be Euler product. Okay, so you got two things which is may not be think they are related to each other. Okay, so this is a theorem that we want to prove. So let's suppose that f is let's suppose f is complete multiplicative. So multiplicative means that I think I also said this before is f of m n equals to f of m if GCD of m n is 1. So if they are compared to each other, which is 1. Okay, and then you can try. Okay, so now in this case, we have if f of s converge absolutely, then Euler products, so Euler product converge, also converge absolutely. Okay, the second one is that this f of s converge absolutely if and only if this f p to the m, p to the ms, p to the m less than infinity. Okay, which is this one, right? This sum. Put into here, so f p to the m, p to ms. Sum is, I think this sum is what? Oh, this sum should be all of p. Okay, so sum over p, f p to m, p to ms, that's infinity. Okay, so that means if, okay, let's just do the proof. Okay. Oh, by the way, I forget about if f of s converge absolutely, the Euler product will converge absolutely then. And also f of s will equals to the Euler product. Okay, so basically, if f is completely multiplicative, then these two will be the same. And if this guy converge absolutely, and f is multiplicative. Hopefully it's trivial. Okay, so let's do this one first. Try to compute this. We take absolute value. This guy will less equal to p, and from 1 to infinity, f of p to m, p to ms, which is less equal to n from 1 to infinity. Okay, because I take, so I sum from prime, so I sum from all the integer, which is f n of s, n of s. Okay. Okay, so now if the original series converge, then this guy will converge. Okay. So this is what the first one I want to show. Okay. So this is so what you prove is this is general criterion for infinite product. Okay. So this is mainly that we almost prove our results. Okay. Okay. This is just the sketch, but you know how to prove it. Okay. And since it's multiplicative, right? So since it's multiplicative, so I think it's very trivial that you can write that's right. So since this is multiplicative, so you can write f of n in terms of prime power. Okay, so you can let's say n is a p1 m1, p2 m2, let's say pk mk. Okay, and then you get p1 m1s, p2 m2s, pk mks. And this sum can be sum all the primes and all the power. Okay, so all the power m1 and 2 up to mk. Okay, so it seems like a larger sum, right? But you can separate this in terms of f. If you do this, then you will find this. you will find that, oh, it's separated, right? So it becomes times. Okay, then you can separately sum into products. Okay, into products. So which is your sum over primes, which fp to m divided by p to ms. Okay, so which you guys Euler product. Okay, so one quick example that I just quickly show this. Okay, because the formula is previous. The previous I already showed the formula, so let's quickly see the standard zeta function. We'll give you the what, so you can check this. This. You can say that it's just all the products, right? So you can write it as 1 plus 2s, 4s, 1 plus 1 over 3s, 9s, plus 5s, 25s. Okay, so this is 1 minus 1 divided by 1 minus this. Okay, so which you can show this zeta function is all the primes, product of all the prime, which is 1 divided by 1 minus p to the negative s. Okay, so this is the famous Euler product. Okay, so yeah, if you just plug the formula that I show this, which fp to the m in this case is 1, so 1 divided by p to m of s, and you write down the infinite series, and then you divide by, you just change it. Okay, so you get Euler product. Okay, so this is the Euler product of zeta function. In the next video, that we can start prove something interesting. Okay, so and now I think I will skip the analytic property of the Dirichlet function and just talk about results, because I think prove this is quite boring. Okay, but I will still say something. Okay, see you guys.